Got it. Thank you.
Okay,
Thank
so
you, John.
my little Tasco telescope, when I saw Saturn for the first time, that was it. I was locked into it. And I'm going to go into that. And I as a result of my long interest in astronomy and optics, I started my company Spectrum Thin Films 32 years ago. And I'm the only company on Long Island that survived optics and optical coatings too, which is I'm proud of that part of it. So I'm going to go over that. This is more of a tutorial than a lecture. And what we're going to do is after my talk, I have a demo here. In order to do that, I'm going to need everybody to go in a circular pattern, and I'm going to take this table in the center of it so you can see the demo of what I'm talking about, okay? And it's really cool setup when you get to see that. So I'm going to ask you questions, and if you guys answer the questions right, I am going to give you Spectrum Thin Films pencil. And I was like a think tank back then. You know, I came up with this idea too. Pink Floyd, Dark Side of the Moon. I love Pink Floyd, and I remember the light going through it and the prism and the light spreading. I said, that's a good idea. So all my company logos and everything on my brochures and website has the spectrum on it. And if you look at my pencil, you'll see a lens, and the light gets refracted through the lens. It goes through it, and here's my logo. I came up with all that. So I will ask you questions as we go along. So let's get going here because we're running out of time here. So this is the one of the telescopes my parents bought me. I think it was at A&S in Hempstead. At that time, A&S in Hempstead was selling astronomical telescopes, and in that time, and my parents used to shop at A&S, and they knew that I was a little strange. My father was a contractor, and my mother was a housewife. I was a little strange because they gave me toy trucks I didn't want them. They wanted space toys. Yes, I was. I only wanted space toys. So they bought me this little telescope, and then I went ahead and I was using it, and then what happened was I asked my parents to buy me a larger telescope, and now I'm 12 years old or something like that, and my parents says we can't afford it. So what did I do? I went to the library. I lived at the library, and I read about building telescopes. Back in those days, there's no one I can talk to about telescopes or building telescopes, and you can't even buy one really. So I went ahead and I built a 10-inch f6.5 Newtonian telescope when I was 12 to 14 years old, which is unheard of, and I ground and polished the mirror to an A-sphere, and that's an image, actual image that I took of the parabola of the mirror that I did. I was like 12 to 14 years old when I did this. I don't even know how I did it. I mean, and it worked. After the telescope was built, there's a telescope after the telescope was built. So I got everything donated, okay? My father was a contractor. This is a sonotube. They pour these concrete footings that you see on the road. That's where that came from. This is plumbing fittings here that my father used for the plumbing, doing plumbing work. So I got that. I figured I can use that for a strap. My father worked in Manhattan on the high rises, and he brought this big plumbing pipe here, the pedestal from Manhattan, to me to do it. And he got me all these plumbing fittings that you see here. And I made this. And then I took, back in those days, my father used to do plumbing work, and he had this vat that melted lead for doing plumbing work back in those days. I said, I can use that. And I got a coffee can, and I put a pipe through, a shaft through it, and I filled it up with lead. I don't know how I figured out how much counterweight I needed and everything, but I did. That's all I can tell you. So this is a telescope I built, and I completed this telescope when I was 14 years old. Pretty much everything was donated. The grinding and polishing machine material was, and the mirror was a company called Universal Photonics, and they're still on Long Island, and that's what they sell, grinding and polishing compounds. They're right here on Long Island. So
Picture taken, Tony. It looks like it's
this picture was taken to Capchat, Canada, where my father we were going to photograph the total solar eclipse, and I brought that big telescope to photograph it. So that's where that is. Yeah. So So this talking about optics, we work with an astronomy. Now you guys have telescopes, you have refractors, you have Newtonian, you have celestrons, you have Meads, but you may not know exactly how exactly it works. So tonight I'm going to be talking about that. So I'm going to be talking about the refractor single, dual, and tri-element lenses in a refractor, reflectors, Newtonian, cascade, mirror lenses. Now, I am only scratching the surface. If you want, I can give more detailed talks on each item at a later date, like on Newtonians and then refractors at a later date. So I'm just basically going over that. Now, eyepieces, simple Galilean plastels, and more advanced like Teleview eyepieces. Al Nagler just recently passed away, which really saddened me, and he revolutionized the eyepiece industry. He will go in history for what he's done. I'm going to just touch on his eyepieces because they're really complicated. Bolo lenses, variable eyepieces, and there are tons of eyepieces with very different configurations, and I'm only going to go through some of them. All right, so refractors now. So basically, which I'm going to be talking. Oh, I'm also going to talk about the history of telescopes, also. But originally, when they were first had telescopes, they basically had a what kind of lens is this? There's a question. Who knows what that lens is? All right, you get a pencil. Okay. Now you're out of it now because you got it. Now, what is this? Nope. Plano concave. All right, Ken gets it. It's a plano concave lens. So what that does is it causes you to focus the image, but this is a very crude telescope image-wise. So basically, I don't know why I got all this stuff on top of here, but anyway, shows a telescope made of two lenses, the convex objective and a concave eyepiece. The same construction. What are you doing? Oh, I see. Okay. I knew it.
Tony, talk.
All right. So at any rate, so I got to see it. I can't really see what you're doing here. All right. So the same construction used by Galileo. Galileo used a simple lens for his Galilean telescope, which we're going to talk about later on. So basically, all right. So this is you already said this is a biconvex lens. What is this? What kind of lens is that? What?
Double concave.
Biconcave, but it's also called a
Negative?
negative lens. You get another one. All right. You already got it. Yeah.
Yeah.
Now this is a negative lens. It's a biconcave lens. So, and in this configuration, you have two biconvex lenses here. Now the image here is erect, and now it's upside down because of this configuration here. Oh, why am I not going here?
Yeah.
Now I'm not. Now it's you did something. It's not allowing me to skip. Whatever you did.
Yeah. Try not to.
All right. So, all right. So, a two-element lens is like what Ken was talking about last time that he got. I actually worked for Jaegers Optical before I went to college, and Jaegers Optical back in the 70s manufactured one of the best astronomical refracting lenses that were made at that time. They were basically two-element achromat lens, they made 3, 4, 5, and 6-inch achromatic lenses, and that's what I was working on. The objective used was a crown and flint glass, which we'll talk a little bit that later. There's a crown and flint. One's a higher index and one's a lower index glass. Oh yeah, one's high index, the other was lower index. These two-element objectives will only be corrected for two colors. So basically, it can be corrected for the red and blue, but you're not going to be corrected for the red. So in layman's term is that, for example, with that telescope, and you looked at the moon, for example, you may see a red fringing because it's not correcting for the the red color. Or if you look at Jupiter, which is bright, you'll see a red fringing on it. So that's what that is. Okay, achromatic doublets for aberration correction. Problem, a single lens causes chromatic aberration with different colors of light focused at different points. So originally when they came out with a refractor, it was only one element. And I'll tell you why there was one element, and I'll tell you who later on who actually invented all that stuff. Two lenses with different index are used, a crown glass element with low dispersion glass and a positive with a positive focal length. A flint glass element with a higher dispersion and a negative focal length. So basically what this is telling you that the achromatic lenses being two elements, how they came together. Now some are air-spaced, and that means that you have two lenses that are spaced are spaced separately, and there's air between it. But there's a small gap between the lenses, but it has 4 optical coatings, while the cemented lens has only 2. Cemented means they cemented together. You only AR coating on the exterior because the glue optically matches the 2 glasses together. But it doesn't match it perfectly because they're different index, and that's another story. And a Cleveland design uses 2 positive convex lenses, typically for high power application, and produces an inverted image. Galilean design uses a positive objective lens and negative lenses and produces an upright image commonly used in spy glasses and opera glasses. All right, so here's a good image here. So this is a achromatic lens, like I said, Jaegers made in the 70s. So you got a crown, and there's your flint, the high index, low index. And when the light comes in, so the visible light is red, green, blue. Okay, when the visible light comes in, you see what's happening here? It gets refracted. Does anybody know what happens when you take a stick and you put it into water? What happens? What?
It looks like 2 pieces.
Right, all right. What happens is what happens is the index of refraction, not to go crazy with the physics and mathematics, but the index of refraction in air is 1. Water, the index of refraction is 1.33. So the light gets refracted when you put it in the water. So next time now I know all you guys are going to get it. When you get near the water, you're going to stick a stick in there so you can see what I'm talking about, because the index of water has a high index of refraction in the air, so it gets refracted. So what happens is the light comes in, gets refracted, and this refraction is directly related to the index of the glass. And then it goes to the next one, and that gets refracted depending on the index of glass, and it comes to a focus. But you can see that that not all the colors are going to focus at the same. This one here, the green, is not coming into focus. These are focusing here, and the green is off a little bit because the telescope is a 2-element lens. Now, I'm going to step ahead a little bit. They do have a pochromatic lens, which means it's fully corrected for 3 colors, and they still use 2 elements, but they're using a different type of glass that allows that. And I'm not going to go crazy on that. So basically, a pochromatic lens is a 3-element lens, fully corrects the lens. So this is a 3 elements, okay? So you got a biconvex, biconcave, and a plano convex lens. When the light goes in, you see they're all bending through the lens. It comes back, you see it all comes back to the exact focus. A lot of the refractors that you buy today are apochromatic, or not. In fact, most of them are sold today are apochromatic. The lower cost ones will be, will be an achromat. So now I'm a little ahead of myself here, but this is a cast grain design. So unlike the refractors, the problem with the refractors are that you're limited to the diameter, because as the diameter refractor gets bigger, the more expensive it gets. This is before imaging, when you're doing visual observing. So if you have a 6-inch refractor and you have a 12-inch reflector, you're going to see more of deep sky objects. But if you want to look at the planets, and you have a 6-inch refractor with a longer focal length, that will perform better on the planets. So the Cassegrain telescope is a telescope where the light comes in, it bounces off the mirror, hits a convex secondary, bounces off of that, and it comes to a focus here. Now, it's corrected by the shape of both these mirrors, and they can vary depending on each configuration. So that's just a Cassegrain. This is just a rough idea with it. Now, here's the question. What is this?
Eyepiece.
No. No,
A double gas optic.
no.
A screenshot.
It's a lens design software. So
No.
I can't tell you what this is because this I can't tell you what this. What happens is when a lot of these telescopes are designed, a lot of them are done with lens design software, and this is just a screenshot of one design of whatever it is. I have no idea what it is, but they. What does it say?
Double gas stuff.
I don't even know what that means. Yeah, I know. But the thing is that the ZMAX is one of the most popular lens design softwares that is available professionally. There's a lot of lens design software you can get as a free download. I don't get involved with that. I don't get involved with it. I don't know much about designing. This is not my my forte here. But just to give you an idea with this with the lens design software that it goes through a lot of number crunching to come up with very elaborate things, especially the eyepiece designs today. They have to have the lens design software to design a lot of these elaborate eyepieces have today. And when passed through a lens, the light is refracted at different angles with different wavelengths of light. This reflects focal lengths that are dependent on the color of the light. So, for example, at the focal plane at an image, may be focused at the red end of the spectrum, but blurred at the blue. This is what I was trying to explain to you before. So basically, if you have any of your refracting telescopes and you're observing it and you notice color, because that means that telescope is not fully corrected for whatever reason. Some of the telescopes that may be lower quality and they may make it that is an APO refractor, but it's still not being fully corrected. So basically, that's going to cause the blurred image. And the image of the star can appear blue in one side and orange on the other side, or different colors. Refracting telescope with non-achromatic objectives were constructed with a very long focal length to master chromatic aberration. So basically, what that's saying is that if I had a 6-inch refractor, but it was f/15, you may not notice much color coming out of it, even though it's a 2-element lens, but the focal length is very long. So you may notice that. So that's basically what that's saying. An apochromatic telescope uses an achromatic lens to correct for this. So I can't read now. Oh, now the full correction. I know you've been waiting for this thing. This is a full correction lens, a 3-element lens known as a triplet. Okay, a lot of the apochromatic refractors could be either a doublet or a triplet. The doublet uses like an FPL glass or a calcium fluoride glass, which is a special glass that's very expensive. They'll allow these 2-element, but most of the like the astrophysics, I think. Well, I'm not even sure. A lot of them using are using 3 elements, known as a triplet. A sophisticated optical design uses a high-end refractor telescopes to correct multiple optical aberrations. A standard triplet is a apochromatic lens that brings red, green, and blue light wavelengths to a near perfect common focus, resulting in a sharp, high contrast color image. Ken, why do you want a apochromatic telescope? You know, he does imaging. If that telescope is not, if the colors do not come perfectly into the same plane, all right, his images are not going to come out good. So in today's market share, where a lot of people are doing imaging, this is critical to have a apochromatic refractor and a good one.
Yeah, especially that's good if you do color, black and white color and using filters.
Yeah.
green filter, the blue and the red,
Yeah.
and you don't have, you keep changing, doing the color imaging, you don't have to change the focus, it all should stay the same.
Right. Right. Exactly. All right. So the primary aberrations are corrected by a triplet. A triplet lens is the simplest design that provides enough flexibility to correct 5 primary or solidal aberrations for a single wavelength. So basically, a triplet, when they're manufactured properly, they do a lot of correction. Chromatic aberration, unlike cheaper 2-element achromats, which only correct for 2 wavelengths, a polychromatic triplet virtually eliminates the secondary spectrum, the visual color errors that causes colorful halos or fringes around bright objects. This is achieved by using different types of glass with varying refractive and dispersion properties, often including 1 or more elements made of an extra low dispersion glass. This gets a little bit above everybody, but basically what that means is that when they design these lenses like astrophysics, William Optics, they are designed to make sure that they're designed properly. Spherical aberration. Who knows what spherical aberration is? Anybody know what spherical aberration is? Spherical aberration, this occurs when light rays that enter a lens near its edge are focused at a different point than those entered near the center. The combination of convex concave elements in a triplet is specially designed to correct for this, ensuring single sharp focal length. So a triplet refractor that you would buy has to correct for spherical aberration, especially if you're going to do imaging. Coma. Coma is an off-axis aberration. This is an off-axis aberration that makes stars appear comic-shaped as light passes through the outer parts of the lens. A triplet design can effectively counteract this from distortion. So a good refractor will eliminate coma. These are things you should know about because if you plan on buying a telescope, you want to make sure it's the right one for you. So I'm trying to explain to you what they are. So basically, coma, here's a light coming through it, and you're getting this coma effect because of the aberrations of the lens. So this is coma and what it looks like in focus, out of focus. This is slight, moderate, severe. Okay. You can get slight coma with some apochromatic refractors, depending upon what model company you bought it from and how much you spend for it. The rule of thumb is that the more money you spend, the better quality you're going to get, generally speaking, and the less money you spend, it's possible you may not get all the good things you need. Astigmatism, this is not good. This aberration causes points of light to be focused as lines instead of points. This is worse at the edge of the field of view. The advanced optical design of a triplet helps to minimize astigmatisms across the entire image. So these are all aberrations. If you're doing imaging, you don't want any of this stuff we're talking about. And if you buy a better quality refractor that you research at, it generally speaking, it's going to correct for all these things we have here. Now, including this field curvature. This aberration causes the focal plane to be curved instead of flat, result in a blurry image around the edges if the center is in focus. Triplets with an airspace element like the famous Cook triplet design. I know Cook. Cook was an optician and a lens designer years ago, and he wrote the Cook optics cookbook. And I don't even know if I still have it. I may have it at work. So they named this after him. And so it can be optimized to produce a very flat field of focus. You don't want field curvature if you're doing imaging on a really good, on imaging. So, okay, now eyepieces. Here's the complex things. There are a million eyepieces out there. I don't understand, like, how could they sell as many eyepieces that are on the market today and make a profit because there's so many of them. So Al Nagler started the next generation of eyepieces with viewing angles up to 100 degrees. So these designs are very complex. I'm not going into them. These are So I met Al Nagler when I was 16 years old at Stellafane. And when I was 16, the eyepieces were 1.25 inches. They were this big, this small. That was the eyepieces that you were going to get. There was one other eyepiece I'll talk later on. The government made an Urkel eyepiece, and I'll discuss that later on. But all the amateur astronomer eyepieces were this big, all right? I go to Stellafane, and I happen to see Al, and he has this aluminum thing he's holding in his hand. I said, what is this? He says, there's an eyepiece. I says, that's an eyepiece? He says, yeah. I said, this thing is like this big and this round, it's 2 inches and stuff. He says, yeah. So I just designed this new eyepiece. I said, oh, that's cool. That's all I knew. And to realize that he literally revolutionized the eyepiece. So I saw his first version of eyepieces when he brought it to Stellafane. All right, here's a question for you. Which eyepiece you want? Now, these are all different types of configurations of eyepieces. Back in the day, I remember orthoscopic was one of the common ones. Kellner, where's Kellner? Yeah. Kellner, was a popular one. Plossels were very popular. Plossels were like one of the most popular ones they had there. So these are, okay, here's the Urkel. Now, I can tell you about me and my vintage, that the military was using Urkel eyepieces in the military, and they became surplus. And I was able to get that eyepiece. I bought the surplus, it was, and then I had to make a mount to fit into my telescope, and that was one of the best eyepieces of all time back then. It was 60-degree field of view, if I'm not mistaken, and this was the best eyepiece ever. And I remember using that eyepiece at that time, and this is one of Nagler's Type 2 eyepieces, just one that he did, and there's another one that he did. So I mean, he's got so many designs. He's got some patents, but not all patents, Al Nagler. So I'm not going to go through. I'm just giving you an overview on eyepieces, and you know, personally speaking, I have a 28-inch telescope, and I have all the eyepieces, and they're all 100. I have all 100-degree eyepieces. They go from 4 millimeter all the way up to 20-something millimeter, and I use a 20 millimeter 100-degree eyepiece almost all the time on my 28-inch telescope. But I really like the 100-degree eyepieces. Actually the 100-degree eyepiece was developed at Teleview Optics by a guy named Paul with Al Nagler. And Paul passed away too, young, and he was the nicest guy in the world. I helped him coating his mirrors, and he's the one that designed the 100-degree eyepiece, and nobody else had a 100-degree eyepiece. So it was revolutionized astronomy once again, and Teleview was the one selling it. They were the only ones doing it. So here's the Urkel eyepiece I talked to you about. It came out in 1923. So that's why the military were using it. The military wanted this eyepiece because they were going on tanks, and they were going on ships, and they needed the wide field because this has a 60-degree field of view. So they spent a lot of engineering work to develop this eyepiece, and this eyepiece was basically built into their periscopes or whatever they were doing in their for the Navy and whatever. All right, so these are some of the eyepieces. You got the Celestrons, you got all of these eyepieces. Back when I was talking to you before, back in the 70s, this is the type of eyepiece were being sold. That size. Not these, just these little ones here were side. Teleview was the first to come out with the 100-degree eyepieces, and this is the Ethos series that he has there. So I have Stellaview eyepiece set. So I have a whole set I bought from Stellaview, and they're a lot cheaper than Teleview, so that's why I bought it. Although I have Teleview eyepieces too, but these are beautiful eyepieces. They really are, and highly recommend if you have a Newtonian telescope, get a 100-degree eyepiece. You don't need to get a lot of them. Get, maybe one or two. I mean, and there are a lot of companies now selling them fairly inexpensive. Stellavue is one of them. You may be able to find others that sell them pretty inexpensive. So we're not going to go through too many eyepieces, but there are eyepieces used for planetary viewing with higher magnification. That's why he's got a 4.7 millimeter ethos, a 3.7, which I think is too high power. I have one like that too. But when you do planetary viewing, you can use them, the higher power eyepiece for that. Any questions or anything? Okay, so now we have the Barlows. So Barlows are basically, they have two times and 3 times Barlows. They may have a 5-time, but I know 2 and 3. And all this thing does is just multiply. This is a 4-element. They come in different elements. This is 4 elements. Some are 2-element. And this multiplies the image by 3 times. But so, for example, if you're going to go look at a planetary, Jupiter, and you only have, let's say, a 20 millimeter eyepiece, you can put this in and it's gonna magnify it. So that's what a Barlow does. Barlow just multiplies things. So these are common design eyepieces. Back in the day, I talked about it. Orthoscopic was very, very popular. I remember. The Orphels, I remember the orthoscopic and Plossels and Kellner. So 1, 2, 3 are the ones I remember. And the other ones are there, but I don't remember too much about them. So just to give you an idea, this just shows you what they look like. The different configurations of the eyepiece. So how does an eyepiece work? So the light comes in from the telescope, and there's your eyepiece. And then the image comes back here, and it illuminates your reticle, okay, and your eye. Now, here's the thing that you have to understand, okay? If you're young, the pupil is big. As you age, your pupil gets smaller. So you can theoretically get an eyepiece where, you see, this doesn't come directly to a focus. It's going into your eye, and your eye focuses it over here. So if this image coming in is bigger than your eye, then you're stopping down your telescope. You understand? So you got to be careful. For example, like a lot of times if you get, let's say, a 30 millimeter, eyepiece, all right, and you put in a telescope, the image scale is much bigger than your eye. Now, if you're young, it's okay. But when you get older, your pupil gets smaller, and now you're actually stepping down your telescope. Could you believe that? What? You're wasting light. Yeah. So you have to look at so that's what I'm trying to tell you. You got to look at, you got to look at that, and when you're buying something too. And all right. Now for the mathematics now. Let's see how many mathematical people here. All right. And we're going to I'm asking you a question. What is this used for? What is the parabola? What is that used for? What? Why do they use parabolas? No. What? No, but who uses parabolas?
Mathematicians.
No. What telescope uses parabolas? All right, I'll say it that way. Right. What type of reflector? Newtonian. Okay, so you get one. All right. Newtonian telescopes are, which we're going to talk about them in more detail later on, uses a parabola to correct the image, okay? And we'll talk about that a little bit later on. We're going to get a little more challenging here. You got a lot of smart people here. Who would use a hyperbola? What telescope would use a hyperbola? I'll give you 2 pencils so you can figure it out. And you know the telescope. What? Some RC telescopes or Smith-Cassegrains will use a parabola. I mean, a hyperbola. I think are actually RC telescopes are the ones that will use an RC, oh, shit, hold on. Ritchie Kittrand telescope will use hyperbolic. I'm sorry. What did I say? Ellipses? Oh, no, I'll use hyperbolic. Okay. Who would use an ellipse? All right. A lot of the Cassegrain telescopes are configured differently. So, and some Cassegrains will use this. Cassegrain has a primary mirror and has a convex secondary. Some of them could be hyperbolic or they could be ellipsoidal, depending on the optical design. Now you have a circle, which is a spherical mirror. And what uses a spherical mirror that telescopes that's commonly used? No, mirror. What telescope commonly uses a spherical mirror? A what? No. Well, that's not the one. No, that's maybe. All right, she's not that far up. But what the Maksudovs are generally not like common. What common telescope uses a what? Right, like the Celestrons. Right, correct. You got that right. The Celestrons, which I'm going to talk about too. You got to pass this down to him. He gets a pencil. So the Smith Cassegrain, yes, uses that. So these are conic sections that how our telescope works at, okay, mathematically. There's mathematics behind all of this stuff here. The parabola, hyperbola, ellipsoidal, there's crazy mathematics. We just coded at work today. The guy drove down from Maryland. The mirror took him 10 months to make. He drove down here and waited for us, and we coded the whole optics, and I sat down and talked to him, and the mirror is a parabola, but it's not quite a parabola, and they have to program the machine with all the mathematics because the mathematical formulas are related to hyperbola, parabola, ellipse, and circular, and that's what he was going on. He was talking to me about that. Okay, so let's see. All right, so now. So we have a Newtonian telescope. All right, here's a question. This primary mirror, what's the configuration of that primary mirror?
Concave.
No, yes it is, but that's not the configuration. What's the configuration of this primary mirror? We already discussed it. Part of the conic sections we just discussed. Parabolic. Oh boy, this girl's on the roll. I got to give her another pencil.
Oh, for
Judge,
ones, there's.
you got to, she's got to come up here and talk. All right, I'll give you another one. All right, yes, the Newtonian telescope has a paraboloidal. Newtonian has a paraboloid mirror, and this is the secondary mirror. What shape is the secondary mirror? Flat. Okay, you got it. I heard him there. It's a flat. Yeah, the secondary mirror is all right. All right. Here's another question. This secondary mirror, what shape is it in? Ellipse. All right. Bill got that one. It's an ellipse. All right. It's an ellipse. That's right. All right. Here you go. All right. It's an ellipse. All right. So basically, the way this works is the light comes in, reflects off here, comes back, and rounds up, and then your eyepiece over here. Now, when you build a telescope, you have to put this in exactly the right spot so this illuminates the secondary mirror just right and reflects the image that way, okay? And we're going to talk about something really cool later on. Okay, so this is what a parabola looks like when it's fully corrected. It's an image of it, of a parabola. So what happens is when they manufacturing an astronomical telescope mirror, they grind and polish the mirror. Now, you have a sphere, what does a sphere mean? Sphere means that the shape is consistent along the way. A parabola means that it's called an asphere, which means that it's not consistent along the way. It changes its shape as it goes along. And that's what that's showing there. So Newtonian telescope is an aspherical mirror, and it's called a parabola. Okay. So what we were talking about before is that this is the Cassegrain. So this configuration could make this could be spherical, concave. This could be hyperbolic, or this could be spherical. This could be paraboloidal. There's different configurations that a Cassegrain telescope. Now, this Cassegrain is not the Celestron and Me telescope. This is a Cassegrain. It's different. It doesn't have a corrector plate in front of it. So a Cassegrain-based design is where all the light comes in, it reflects off the mirror, it comes back, and this mirror again has to be an exact spot where it illuminates this mirror, but yet the image comes back to the focus point where your eyepiece is. So there's a lot of mathematics calculations you have to do with the focal length of the primary mirror and the convex secondary mirror. I made this thing in high school, and it was beyond its time. I made a 16-inch f4 Newtonian telescope and an f16 Cassegrainian telescope all in one. I don't know how I did it. And not only that, this secondary mirror I made, how was I tested? Well, I made this in a concave, meniscus lens, concave convex lens, and I measured it through the back of the lens. That's how I did it back in, I was in 11th grade when I did this. I don't know how I did it. So, so that's a Cassegrain. I'm not really going into, I had other lectures, what I did when I was in school. So anyway, this is a Smith Cassegrain. This is a Celestron or a Meade telescope. Now, this is something very interesting to understand. Now, the window you see in the front, which is a correcting lens in front of your Celestron telescopes, it's very interesting how they make it. It's not a conic section. What I showed you before, the conic section, you got a sphere, ellipsoidal, paraboloidal, hyperbolic. It's not one of those. This is some guys a long time ago that figured this out. Basically, this is like a window, like a BK7 or float glass window. Let's say it's 10 inches in diameter, and what they do is they put it under a vacuum, and they pull a vacuum out at a certain degree. And they polish it flat, and then they leave the vacuum up, and that makes the Celestron corrector plate on there. So that's how they do that. And then the secondary is they put a secondary in the center of it, and it's convex. So this, I believe that this is spherical. This is spherical. So the light comes in, reflects off the primary. The light comes in and it gets some correction from this correcting lens. So the light comes in, reflects in the secondary, reflects through the mirror, goes through here and goes through the eyepiece as far as that goes. Yeah. No. No, the only thing is it does correction. That's all it does. So here's another view of it, more detailed view of it. These are your Celestron telescopes. So this is your correcting plate is here. This is only one, it's not two. It looks like it's two, it's only one. And then this is a convex secondary that's there. And if you look at your Celestron, you'll see just what I'm showing you. This is known as a what? This black thing here. What? Baffle tube. All right, you got another one. I know. That's a baffle tube. All right, why is that baffle tube put in there? Not Frank now. Why is that baffle tube there for? What is the function of that? What? I think Ken got that one. All right. Yeah, it's secondary reflection. You get it. All right. So now this is the Celestron we're talking about now. How is this telescope focused? Two pencils, if somebody figures out.
Slides along the baffle and moves back and forth.
The primary.
Yeah.
Yeah, all right. So basically, all right. So basically, what Bill's saying is that you see this device here? This mirror moves back and forth to focus it. So when you press this focus knob, you're moving the mirror. That's how they did it. And, you know, it's, I don't know why they did it that way. It's really complicated, but they did do it that way, and it's kind of standard they did it that way. But my C4, my Meade 14-inch is done that way, but I have a regular focuser over here that I focus with. And I can use this to make adjustments. All right. Now, what is a Maksutov telescope comprised of? Question. What is the Maksutov telescope comprised of? What's the component in a Maksutov telescope? Anybody know?
What's the component?
Yeah, what's the optics? What optics are in a Maksutov?
Lenses and mirrors.
You're using plural. What is it? What is a Maksutov optics comprised of? That's the question. Anybody know?
A lens and a mirror.
Yeah, lens and a mirror. It's okay. Get the note.
Two mirrors.
Well,
Right.
yeah, well, no, wait. Yes.
I got one already.
All right. So what happens is, eh, yes and no, because the way it works is that the light comes in, reflects off the mirror, comes back, and this lens has a luminized spot on it. So it's the same optic, but they illuminize a spot on that lens, and then it goes here to the eyepiece. So a Maksutov telescope has a singlet lens it's a concave convex lens that's AR coated on both sides. This is illuminized over here. The light bounces that way and comes here to a focus. So that's how a Maksutov lens have. Meade sells, what is it, the ETX telescope? That's a Maksutov, right?
They did sell it before they went out.
Yeah. Meade also, I had the Meade 7-inch Maksutov telescope.
And the C90 is a Mac.
C90, yes.
I start telescope like that.
The what?
That's the question.
Questar, yeah. And they're out of business. I did coatings for Questar. Now they're no longer around. They went out of business. I did all the coatings for Questar. They went out of business. So basically, this is what a Ritchie-Coren telescope is comprised of, this configuration. And the Ritchie-Coren telescope has many different shapes. The concave and convex side are different shapes. This just to give you an idea of Ritchie-Coren. So Maksutov's called a MAC is a catadioptric telescope designed to combine spherical mirror with a weakly negative meniscus lens. So that's how it works. We just saw that. The design corrects problems with off-axis aberrations, Comer found in reflecting telescopes, and chromatic. So it has a lot of advantages to it. And the Maksutovs were designed in the Soviet Union by Dmitry Maksutov. Came up with a good name. So that's why they came up with the Maksutov telescope. So this is what the Meade ETX telescope looks like. There's the lens, and the secondary mirror is here. Light comes in, and then ends up your eyepiece is that way. They were very popular, ETX in its day. I know that. Now the history of the telescope, okay? The history, okay. Here's the question. Let's go back. Who came up with the idea of the telescope? Nope. 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 What year did the telescope come? All right, here's another one. What year did the telescope come about?
Late 1500s.
No, too soon. No, in 1600s, early 1600s. And the history of telescope is in 1608. Okay, which appeared in 1608 in the Netherlands. Okay, so this guy Lipperstein, he made eyeglasses. He came up with the idea of using lenses to focus your eyes. And then what happened was that worked. So he was making eyeglasses. And then he said, oh, maybe I can make something to magnify things. So he made something into a telescope. So it was magnifying things. Well, Galileo took that idea and says, hey, why can't we make an astronomical telescope to look at the cosmos? So Galileo was the first one to make an approved design for astronomy. Yeah. And and Sir Isaac Newton is credited for building the first reflecting telescope at 1668 with a design that incorporated a small flat mirror, blah, blah, blah. All right. And the Cassegrain telescope was 672. As you know about that, and an achromatic lens, which is greatly reduces color aberration objectives, sort of came about in 1733, made by Chestermore Hall. John Dolan, okay, a long time ago, I'm with my daughter's mother, we were dating, and her friend had a little telescope, and he asked me to clean it. And it was brass, it looked old, and I took the lens out, and the lens wasn't even quite round. It looked like it was done by hand. The manufacturer was Dolan. This was a long time ago. The telescope is probably worth a fortune today. Dolan was the, and he was the one producing a lot of telescopes back in 1758, John Dolan. Important developments of reflecting telescope with John Dolan production of a large parabolic mirror at 1721. The process of silvering glass mirrors induced by Leon Foucault, the Foucault tester guy, in 1857. So basically what that says is that when they were making reflecting telescopes, they didn't have aluminizing chambers. They didn't know how to do metallization. They were making mirrors out of speculum, which is a metal mirror, which was reflective. And then they wanted to make it out of glass, so then they figured out chemically they can make silver on a mirror chemically. So that's what that's telling you here. And the average of calcium reflector was invented around 1910. Okay, so whose telescope is that? Newton's. This is actually, I think it's actually a real image of Newton's telescope that he did. And he was pretty brilliant because he had this ball and being held by two spots here so the telescope can move any which way it can. He had this eyepiece here, and the way he focused it over here, if you look at this thing, he had this bar here and this knob here, and he moved back and forth to get focus. So he had a really good idea of making a Newtonian telescope back in those days. This is a small little telescope that he made. I guess that's a mirror. I don't know what that is, but so this is one of his drawings Newton did on developing the Newtonian telescope and the focusing mechanism of it back in the day. So notes on Hans Lippershey, with unsuccessful telescope patent in 1608. The first record of the telescope comes from the Netherlands in 1670, and it was basically from the guy who came up with the eyepieces. I mean the eyeglasses, and he had a patent on it. And but they took his patent and his idea and they modified it for astronomy. Okay, so. This guy, Leonardo da Vinci, I think he's one of the most brilliant people of all time because he was an astronomer, optics. He was what else did he do? Astronomy, optics,
Helicopters.
paintings, okay? This is one of his original drawings of optics for something, whatever it was, but that's original that he did. And he did the Mona Lisa. And there was a picture of him and Mona Lisa, this girl he knew, and he drew this picture of her that became famous. And if he only realized like how much his painting is worth today, he would be astounded. But he was brilliant and involved with medical. He was a painter, a scientist, astronomer, and optics, all in one. I mean, this guy was so incredibly brilliant, this guy, unbelievable. and look at this painting like he did. I mean, I saw the Mona Lisa. It's just incredible. So, and his drawing notes on astronomy. This is the original, or his notes on astronomy. It's not in English, though.
See, he wrote back.
Yeah. Yeah.
Oh, he did.
He did.
So the Galilean telescope, this is the Galilean telescope. Very simple. They probably had a convex lens here, an eyepiece here, a negative lens here. And he made this thing here. You could see it, it looks almost in two pieces here. But that's a Galilean telescope. And Galileo was the one looking at Jupiter and seeing the moons on Jupiter, and he was writing everything down as he was doing it. During the period 1850 to 1900, reflectors suffered from problems with metal mirrors. Considerably number of the great refractors were built from 60 centimeters to 1 meter at Yoki's observatories back in 1897. They were building telescopes like crazy back then. However, starting from the early 1900s, a series even larger reflectors with glass mirrors were built, including Mount Wilson's 60-inch, 100-inch, and 200-inch Hale telescope, which is still being, all this stuff, a lot of it's being used still today, back in the early 1900s. That's it. I'm done.